Looking forward to a great talk. So, over to Ofer.
Thank you, Sri. Hi, everyone. Oh, this is on. OK, great. Thank you. So I'm going to talk about Bayesian networks with R and Hadoop. As Sri mentioned, I'm from Hortonworks. I run our data science team. And previously, I was at a few startups like Nor1 and Risk Insight, also at Yahoo. I was there for about 5 years, working on search advertising and essentially predicting click-through rates for search advertising. So in the talk, what I want to talk about is give you a quick overview of what is a Bayesian networks. It's a complex topic, so I'm going to try to make it short and sweet. And more importantly, why I think it's cool. And I think it's a little bit actually not overlooked. I mean, there's a lot of people focus on supervised learning and clustering, but Bayesian networks, especially in the context of big data, has not been talked a lot about. So I'm going to try to tell you why I think it's important for this particular topic. And then I'm going to go and show you some code around how to use Bayesian networks with R. I'm going to introduce the bnlearn package and show you some example code. And then talk to you about how you do inference with R and why Hadoop can be helpful with that. OK. So to start, what's a Bayesian network? Very simply, it's a DAG. It's got nodes and edges, which makes it a graph. And the nodes are random variables. They take discrete values. You can also have Bayesian networks that are continuous, but I'll talk more about discrete. And the edges are essentially represent conditional dependencies between the nodes. And then you have a certain conditional probability table for each of the nodes, which essentially represents the probability distributions, the conditional probability distributions of a node given its parents. So this is what it looks like. You've got a bunch of nodes, and I've picked a very common example in all the textbooks. It's called the Asia example, and it's from healthcare. So you have somebody could have visited or not visited to Asia. Here, all the variables are actually binary. So you either visit or didn't visit Asia. You might be smoking or not. You might have tuberculosis. So a lot of different nodes, and then the arrows are essentially represent conditional dependencies. So if you have an arrow, for example, between let's say tuberculosis or cancer, from lung cancer and tuberculosis, that represents that this node is only dependent on those two nodes and no other, okay? And then finally, each node has this, and I'm sorry the arrow is not showing very well there, but it's got a conditional probability table. So you can read that as in row 1, if tuberculosis or cancer is true, bronchitis is true, then shortness of breath might be 0.7 if it's true. Those are the probabilities, 0.7 or 0.3. For those of you who notice, this is a funny joke in the healthcare community that there's a lot of words that are kind of, for a layman, might be interesting. Shortness of breath is SOB. So there's other jokes like that going on. Anyway, so let me talk about why I think Bayesian networks are cool. Okay, there's 3 reasons I want to talk about. One is it's a very intuitive tool for modeling real-world problems. Because you think about nodes, what you care about, what you don't care about, and how you put the graphs, how you put the arrows to generate a graph. So it's a very natural tool to model. And it allows you to also include both things that are learned from data, but also include experts. So in the case of healthcare, for example, you can have experts tell you what the dependencies are. This depends on this from a clinical perspective. So in any topic you want, you can actually include both data-driven and expert knowledge sort of in the same model very easily. The second thing that I really think is very, very interesting is the fact that we can actually infer with missing values. And that's really important. So a lot of supervised learning model where you want to do predictions, you have a features vector and in your feature matrix, and you kind of gonna have to have every one of those values. And if you don't, you're kind of stuck. Some algorithms treat that differently, but most algorithms actually need to have all the values, and if you don't. So in a lot of real world examples where I come in with our customers, for example, missing values is a very common phenomenon. For example, again, I'll go for healthcare because we stayed in that. Imagine that you want to predict somebody has diabetes. A good valid value would be their glucose lab result, which is a very good indicator of whether somebody has diabetes or not. It's actually a good indicator, right? It's a deterministic indicator. But let's say that you want to use that. Well, what if a patient did not have the lab? What's the right value? It's not 0, it's not 100. I mean, you can't guess, you just have to have the value. So in supervised learning, people had other ways to deal with this and some estimation, things like that. But the cool thing about Bayesian networks is you don't have to do that. There's a kind of an implicit way to deal with missing values. The third thing is that actually you can build a model and you can ask questions or make predictions on any one of the nodes. You don't have to build a model per target variable you define for your problem. So that's also very cool. Okay. So, if you look at the history, Bayesian networks are not new. They've been around for many years. They've been used in a lot of different areas, in healthcare, in education, in finance, even tech support. I saw that in some place where I think Microsoft did a lot of research in using them in tech support and trying to figure out what's wrong. If you're interested, there's a reference here for a book that has a lot of different applications, a lot of detail if you're interested to read some of those. Now let's move to, I want to talk about how you do Bayes network analysis in R. Okay, so R is, of course, a well-known package for statistical analysis, and there's a lot of different packages to do with Bayesian analysis in general. Then Bayesian networks specifically, there's also a few packages I've looked at, and there's a few that I've never looked at. But I'll focus on this one called bnlearn. It's written by this guy Marcus Guttari, University College of London. And he's done a pretty good job. And what this package does is it allows you to implement various structure learning algorithms. This will be the algorithm that from data learn what the right arrows are in your network. Then you'll have algorithms to learn the CPTs or the distribution of the probabilities. And then also, most importantly, do approximate inference. So allow to do inference on the network and ask it questions and things like that. So let's see how this works. So again, the first step, as I said, is constructing the graph or learning the arrows. And you can do that manually. In other words, you can tell the network here's what the arrows look like. Or you can learn it from data. So if you want to learn it, you build it manually. Of course, that's very easy. This is an example. You create the variable names. You create an empty graph. And then you say arcs for this graph are a bunch of two vectors, one of the from and one of the to, and you just build the graph. And if you plot it, it looks like this. Okay? Very simple. If you want to do automated learning, then again, I give it the variable names like this. The third line says data Asia. I mean, actually, Asia is a data set that's available in the bnlearn package, so I just downloaded it into a data frame. And then I use this algorithm called HC. That's one of the learning algorithms available. It stands for hill climb. And what it does is it looks at the data set and it tries to learn automatically what the arrows need to be. Okay, there's a bunch of others. If you look at the package, you'll see there's maybe 5 or 7 different algorithms you can use and plot it. And some of you might notice that this graph looks a little bit different than the previous slide, which is a very common occurrence because this learning is not a brute force. It's a approximate algorithm, and so depending on where you start, it might give you different results, which is very important. It becomes more important when you go to larger scale. But automated learning doesn't always work perfectly, right? Sometimes you don't learn all the expected edges. Sometimes you learn edges in the wrong direction and things like that. So in order to really make this work, there's two things you can do. One is use whitelists. So whitelist is, again, available in the bnlearn. It was very, very helpful because you can say these arrows have to be in the network. So learn everything else you can, but as long as it's a constraint, as long as these arrows are in the network. The other one is a blacklist or a negative constraint, which says learn the network as long as these arrows never are in this network. So for example, if you find that you learn arrows in the wrong direction, you can just put an arrow in that direction, in the wrong direction as a negative, and you'll never learn that. So, and doing this helps a lot. The other thing, and I'm not going to talk too much about it, but it's also ensemble learning. So for example, you can, using boot strength, but the way you do this is you say, I'm going to learn the network from a sample of the data randomly, like 100 times, and I'm going to take the arrows and vote on only arrows that appear more than, let's say, 85% of the time. I'm going to have them, and the rest I'm going to forget. And it helps with some of the chaotic nature of this that happens. But generally, this works pretty well. So imagine we learned the arrows. Now we need to learn the conditional probability tables. And again, I want to make a note about these conditional probability tables. It really depends on the fact that there's not too many arrows coming into each node. If there's 1,000 arrows coming into each node, I mean, the complexity, it's exponentially large, and you can't really do that in a reasonable computer system. But again, in R, how we do it, this is one function, one line is actually bnfit. There's a couple of parameters you can set to that, but generally you give it the DAG, you give it the data you have on these variables, and then it learns the probabilities automatically. As you can see, if you print it, you see that in this case it's a very simple something you can print. If it's got 10 variables, the printout will be much more complex. But it learns the different probabilities. And then, now we're getting to the fun part. Now you got a network. This is called a Bayesian network that's fully learned, and now you want to use it to do some good in the world, right? So how do you do inference? Well, the way it works is you say, given some evidence, and the evidence will be a value for one or more of the nodes. In this case, in this example, let's say you got visit to Asia is yes, bronchitis is yes, and shortness of breath is yes. The rest of the nodes have no value that I know of, right? This is why actually it's really interesting for missing values, because if I don't have to specify all the values just except my target variable. I can specify whatever nodes I know the value of. In this case, it's these three. And then I can ask it, what is the likelihood of, let's say, lung cancer? Okay? And it'll give you the probability that lung cancer is yes. Okay? And so as I said, we provide evidence. If the value is missing, which is not included. And this is very important. This is what makes it very, very robust for using missing values. Not a trivial characteristic of a technique. Okay. So how do you do it in code? You call CPOuery. That's the function name in bnlearn. You say the event is shortness of breath is yes. That's what I'm trying to predict the value for. And I give it the evidence that Asia is yes, bronchitis is yes, and I get the value. It has two methods. One is called logical sampling, I think, and the other one is likelihood weighting. Those are two known techniques in Approximate inference, and implements both of these in this case. So we finished how R, how we do R, use R for Bayesian networks with this package, so we know this. Now let me talk about large-scale Bayesian networks, okay? So most examples you'll see are actually relatively small when you go and research this. And by the way, one other comment, this topic is quite complex. Bayesian networks is part of this probabilistic graphical network, and I'll encourage you at the end to go and research this more because I think it's cool, but be ready for a long journey. It's not easy to consume, and it's quite complex. But if you want to do it in large scale, first of all, what is large? Let's ask that question. So my experience and my sort of perspective is number of nodes, if it's, a few nodes, it's small. If it's, tens going into 100, that's kind of medium. Hundreds is already large, is large. And if you get to thousands, that's very large. Number of instances, it could be hundreds of thousands or millions or more, but one of the problems is when you get such a large network, if you want to draw it or something to see the net, or kind of have an expert give you the it kind of looks like this. There's no, right? It's not realistic to do anything other than 5 or 10, So in that sense, so it's a problem. So what do we do? Well, to learn, what I found very useful is you define the nodes, and then you get an expert to give you some seed some of the known edges, right? So you do that as much as possible, because the more you do that, the more the automated learning actually works better. So you want to do that, but you can't do that for everything. But you can, as much as you can, get expert knowledge and seed it, and then use some automated learning, like HC or Taboo or some of the other algorithms available to learn in large scale. Now, what I want to talk about here is not about the learning, but about the inference and how you can use Hadoop for inference at large scale. Now, when you do large-scale inference, there's exact inference and there's approximate inference. I talked more about approximate previously. Exact actually implemented another R package called grain, if you will. And I want to give you like a little bit of why I moved to the approximate as opposed to the G-RAIN. One of the problems is that exact inference in Bayes networks is actually very fast. You know, doing an inference is pretty fast, even in large networks. However, the computational complexity of learning those and doing inference is really determined by the size of what is called the largest click size in the graph. Yes, of course.
The question is, working with all your nodes were categorical.
Yes.
Do you have a continuous field like age or cost? Do you create 5 bins or 10 bins or something?
So you can do that. You can do.
Help what are optimal bins?
There are also possibilities to use a Bayes network with continuous variables. I'm just not talking about it here. But if you want to do exact, you can actually, yeah, you can discretize them in some way, yeah. But let me go back to this. So there's a problem because the way that exact junction tree specifically works is that it's exponentially growth in complexity. So after you get a pretty big network, you're out of luck. So this is why we're using Approximate. Now, to show this, what I've used is I use this package called R Hadoop, specifically RMR in the R Hadoop package. I'm not going to talk too much about it, but you can find more data here. What it allows you to do is to run mapper and a reducer with R code. And this is my plan. So what I want to do is, let's say I want to do inference at a really large scale. I want to infer something about 1 million or 1 billion patients, and it takes a long time. Part of the challenge of approximate learning is it does a simulation. So every learning instance could be maybe a second. But if you do it for 1 million, it takes quite a while. So in order to do that, I want to parallelize it across the cluster. So what I do is I split the instances I want to infer for into chunks, and I send them over actually to the reducers, and each reducer does a CPOuery across. So let's say I have 100 reducers, and I can do 1,000 on each reducer, and then I parallelize it this way. Why didn't I do it on the mappers? Because controlling number of mappers in Hadoop is a little more tricky and it's much easier to do the reducer. So what I did is just as a trick, the mapper gets all the instances and randomly selects a reducer to go to, and essentially it's a no-op. So that's my plan. Let me show you how the code works with that. I chose for this an adult dataset, which is, again, a very old known data set. Again, it's not really large. I know I'm talking about large, but I wanted to make sure that you guys, this is all available on GitHub. You can go and look at it and reproduce it on your laptop on a virtual machine. So that's why I chose something that's large, but not too large. So I got this data set, and essentially the problem there is to using a lot of information to predict whether somebody makes more than 50K or not in a year. Learn the network using one of the algorithms. This is what it looked like when I finished learning it. And then with RMR, what you do is the top shows you a bunch of option settings on how to use it, setting up the number of reducers to, in this case 4, but you can do 100 if you want. And then you run this function called map_reduce, which essentially says here's the input file, here's the output file, and it gives us a map function and a reduce function. The map function is essentially, as I promised, is a no-op. What it does is it allows you to, it just takes the key and the value coming in. The value is the important thing, which is the row of variables here. And what it does is it's essentially choosing a random reducer and just spews it out the same way. So it doesn't do anything, just randomly chooses where it goes. And the reducer is where all the magic happens. Essentially what we do here is we take the row, we split it into fields, we give them names. I call this function called data prep, which is actually, it's on GitHub, you can look, but it does some data manipulation to make things discretized like you actually asked earlier, things like that. And then the bottom part is what's important is I say, well, the evidence I have is everything other than the income. In this case, I don't have missing values, so I'm taking everything as the evidence. And I'm saying CPOuery, give me what's the likelihood of something above 50K, and outputting that result in addition to the original values. And this is what it will look like at the output. If you see there's a number there, 0.37 or 0.14, that's the probability of that's coming out of the network. And this is my output file. So I think I'm running out of time, but if you want more information, I really encourage you to, you can go to my GitHub and look at this project in more detail. The slides are there, the information is there. You can download the Hortonworks sandbox to try it out. And then a lot of information about how to learn more information about probabilistic graphical networks in general and Bayes networks. And I'll take any questions. Thank you.
Thank you.
Thank you, Ofer. Any questions?
Any more questions?
Oh, there's one.
Anyone?
Actually, that data set we also used yesterday for our interactive hands-on session. Remember the 93 AUC? So please go and play some more.
Hi, I have just a couple of questions about.
A little bit closer.
Sorry, I have a couple of questions about
Yes.
these Bayesian networks. One would be how do you feel they compare to other modeling techniques that are sort of parameter, they don't care how the things are related and you let the modeling technique learn it. So things like, how would you compare it to say like a GBM, just run it against the whole data set? And then the second question is, how easy is it to pull out insights about how different things are related to each other, right? So like when you build that network, it's much easier to see that how smoking impacts the two different tuberculosis and the.
Good question. So thank you. So for the first question was like how do you compare Bayes networks to other things? If I lost the
Right.
voice? How is it compared to like other supervised learning models or things like that? I've not been trying to show that this is doing better than something else here. I was just trying to show how to use it. I think like anything else, it's really hard to predict before you know the data set, right? Is random forest going to do better than support vector machine? I don't know. Usually it depends on your data that you have. I think the important thing for me is that this technique is actually something that allows you to handle missing values and allows you to incorporate expert knowledge, which most of these other techniques don't, which makes it very valuable. Now I'm blanking on your second question. Oh, insights, yeah. So I think it's interesting. You can actually take a look at both the CPTs and the learned arrows and use that to gain insight. Now it's careful, you gotta be careful, right? Everybody knows that correlation is not causation, and arrows learned from the data is also not causation. So it's kind of, a lot of times when an expert to give you the arrows, they'll give you the causal arrows that they know from, if it's healthcare, from clinical, whatever. But the other way doesn't go the same way. So you gotta be careful how you interpret it, but it's absolutely interesting and useful to look at. Yes.
All right, thank you very much, Ofer.
Oh, my pleasure. Thanks, guys.